All right, so one other comment I want to make. PA5 is due Friday morning, and normally I like talking about the programs after they've been turned in. So Friday's 11 o'clock class, instead of just being an open lab, I plan to spend at least a few minutes talking about PA5, final questions people had. I'll show you some code that I wrote for PA5 and so on. So that'll be on the video if you can't make it to the 11 o'clock class. There'll be actual information there. So it's not just the open lab kind of thing. So you might want to eyeball that if you have questions about it, or of course, you can catch me in office hours or wherever to go over that. All right, well, let's look at, I guess I don't need the screen capture here. Let's look at the possible topics for final exam. So as usual, not necessarily all inclusive, but I think this is a hit list of most of what we've done. And let me start from the end, because the earlier stuff you've already been using extensively, so it's not as interesting. So heaps, what should you know about heaps? You should know max heap versus min heap, okay? Basic nature of a heap, largest number is at the root. For a max heap, and each node is bigger than its children. For min heap, it's just reversed. It's the smallest node on top, smaller than the children. Up heaping and down heaping. So when you want to insert to a heap, what do? You add your node to the last position in the heap, and then you up heap. You move it up as often as you need to until you've satisfied the heap property. For removing, you remove the root. That's always the largest or smallest, depending on the nature of the heap. You take the last element, put it up at the root, and then you down heap. So you move it down as far as you have to until the heap property is satisfied. So that's the two basic operations, inserting and deleting, up heap or down heap. And those are the same operations regardless of whether it's a max heap or a min heap. The only difference is what is the heap property you're trying to satisfy. Okay, but insert, you always put it at the bottom, and up heap. Deletion, you always remove the root, move the last thing up there, and then down heap. And then heapifying was this tricky way that we had of taking a bunch of data and turning it into a heap without doing an insert and upheap one at a time. You throw the data into an array, into a heap shape, right? And then you begin at the last node and you move through and see if the heap property is satisfied from that point down. And if it is, you're good. If not, you adjust and you move down. So you're doing a down heap from each node. And that's the order n way to build a heap of n items as opposed to n log n. So that's heapifying or heapification, if you like. And then implementing heaps with an array was the last thing we talked about. So that was the idea. If you store your data in an array, you start at index 1, you can do this index arithmetic to find children and parents. And since all we're ever doing is swapping parents with a child, we can do that in an array without moving things around. So it's a very efficient way to implement and manipulate a heap. All right, and then sorting, bubble sort, insertion sort, selection sort. So bubble sort you probably already know, right? That goes back to 121 probably. Insertion sort, you do your sorting based on where you move your number into the output. So your output array is always sorted. Okay, you insert it into the right place in the output array. Selection sort, you select the right number from your input to add to the end of your output. Okay, so it's a question of where you're doing the work. Are you doing it when you insert to the output array or when you select from the input array? And those are both order n squared, typically. Merge sort was a divide and conquer. So the idea was split your set of data in half, sort the left half, sort the right half, and then interleave them together. Pull off the largest or smallest from each array and put them into your output as you move through. The interleaving is an order n operation, and each time that you split your array in half, the things that you're sorting are half the size, so they get sorted with another call to merge sort, and you end up generally dividing your original set in half log n times. Right, so that's the number of times you can cut these pieces into halves. So that turns out to be an n log n. Heap sort, we don't really think I mean, you can do a sort with heap sort, but we usually aren't thinking that. But you could take all your data, you could heapify it into a heap, and then just keep pulling off the root and moving the last node up and down heaping. So you can do a sort like that. Quick sort was the one that we worked through on Monday, right? So you have the two indices, and you have a pivot. Pivot's usually the last element, and you move one index until you reach a number that's the wrong relation to the pivot, and you move the other index until you get to a place that's wrong, and then you swap those two numbers, and then you keep moving. When the two indices meet, you swap that element with the pivot, and now the pivot's in the right spot, so you quick sort the left half, and you quick sort the right half, or the left piece and the right piece. Hopefully they're close to halves. So that's another n log n, typically. And radix sort was based on looking at each digit, starting with the least significant digit, move your numbers into an output, preserve the order of things that have the same digit, then move to the second least significant, third, fourth, and keep going until you get to the most significant digit, and when you're done, everything is sorted. So that was a cornucopia of different types of sorts. All right, dynamic programming, that's what you've been doing for at least the last week or so, PA5. So dynamic programming in general is taking a problem and writing a solution as some function of similar versions of that problem, but with a smaller input set. So knapsack problem, right, is as good as any example. We can find the maximum value for this capacity by looking at the maximum value for these smaller capacities and doing a bit of arithmetic. So we can code it up, and it's just making a bunch of recursive calls to itself, but with smaller values. And if those values get smaller on each call, eventually we'll hit a base case. Like if your capacity is 0, return a 0. And then caching of the results we do for efficiency. So most of these recursive algorithms will end up calling the same cases again and again and again. Right? Fibonacci is a good example of that. Caching, we just save the result each time the first time that we calculate a function value for a certain argument, we save the result. And subsequent times when we look for the function value at that same argument, we'll just pull the result out of memory. So it's an efficiency mechanism. All right, do we remember tries? Feels like it was a while ago. So a try was this.
It's a Scrabble board.
Yeah, it's a Scrabble board.
How many points is that worth?
Scrabble board answer? I give a few points for humor sometimes. I did a calculus test once, and it was like a volume of a cube that was growing or something like that. And there was no answer, but this person drew a noose on the bottom of the cube. And it's like, is that for you or for me? Or I don't know.
Is that a thread or a promise?
Yeah.
It's like a cube doesn't want to grow anymore.
Yeah. So a trie was comprised of these really wide nodes where we basically have a pointer for each character of our word if we're making a trie of words, right? And these are initially null to say that they're not pointing anywhere. And if we have a word that begins with a C, then this node associated with C will point to some other node. And if the second letter of the word was an A, then this A would point to another node. And if the last letter of the word was a T, then the T would point to yet another node. And in this one, this end of word flag would be a 1, whereas it's a 0 everywhere else. And that says we got a cat in our trie. So you can follow the C, A, T, and end of word flag is set, so that's a word. And if you wanted to store C, A as a word, we could also set this end of flag. And that says if you start with a C and follow an A, that's a word in our trie also. So now we got cat and we got California. And it's very efficient for storing and retrieving information and for searching, right? So if you want to search for a word, it's going to take you however many characters are in that word, that many operations. If it's found, if it's not found, it'll probably take you less.
This is all like predictive text, right?
Yeah,
You
yeah.
can store like an entire Unicode library.
Yeah.
You know.
So if you type in a CA, right, this basically tells you how to get to all the possible words that begin with a CA. And you could traverse your structure from this point down and generate a list of all the possible words. So yeah, predictive text, good example.
And it'll select the one you least intended to use.
Absolutely, yeah. And it'll do it quickly so you don't notice.
That's Microsoft's predictive text.
Yeah.
That would be interesting. You could add another, not a flag, but like another
Yeah,
set
counter.
each node that counts. So
Yeah.
each time it gets used, it increases that count.
Totally. That would be a good 223 project too.
We're gonna have like 50.
You're gonna have daily programming problems and they're gonna be
Daily
like,
programming is.
yeah. I just need a way to grade them more easily. Like have each other grade them.
It's literally setting up.
All right, and these are pretty straightforward to traverse also, right? You could write a recursive traversal for this, and it's basically, print out an A. If this is not null, print out an A followed by what you get when you traverse, starting from this node, right? And then print out a B followed by everything that you get by traversing this node, and a C, and so on and so forth. But really, really intensive memory use, obviously, right? Because these nodes are wide. So that's the downside, but the time performance is really nice.
So
Deleting.
what would something like this be like on the test, since we haven't really done any code with it?
So I could give you a picture of a try like this and say, is this word contained in here?
Hmm.
Or modify this to add this word.
Just like the high level concept.
Yeah, high level concepts. Did you have a question?
I was wondering about deleting, but.
Oh, yeah, deleting gets interesting. An easy way to delete is just to clear that end of word flag. But then you've got junk in your structure. It won't do any harm, but it takes up space. And if you want to actually clean that up, you got to do some work, because if we get rid of our catch, right, we could change this to null as long as everything else in here is null. If something else in here is pointing somewhere else, we've got to keep that T. And if we get rid of that T, we might be able to get rid of that A also. So you kind of have to work your way back up and do some analysis.
Worst case scenario, we have to change 26 things to point.
I think it's still based on how long your word is.
Okay.
Wouldn't it technically, like, if you had 26 words that started with CA, or
Mhm.
see, if you had that way.
So if we had 26 words starting with C, each of
you'd
these
only
would be
have two
pointing
pointers,
somewhere.
one for C, one for A, and then 26 for everything else.
Yeah.
You literally just have to get rid of the, like, oh, you wouldn't have to get rid of anything, would you? How would you do that?
So if we're just getting rid of cat, but we got CAA, CAB, CAC, and so on, then we would just change that to a null. Sorry, we change that to a null, and
Free that.
Oh, change the ending character that it points to null?
so if we had a CATT, right, we can't change this to a null, but we can clear that end of word flag. If the only thing that started with CAT was CAT, then we can actually free this node and change this to null. But we can't do that unless we've checked here and made sure that all of these are null, right? Because if anything's pointing somewhere else, then we need to preserve this node, and so we can just clear the end of word flag.
So you guys are going to have like a pointer at the end of it just to be an end of word?
Yeah.
Okay. Cool.
I won't ask you to delete from a try on the test, though.
Are we going to be trying, or wow, are we going to be doing tries next term?
Are we gonna be trying at all?
Are we going to be trying?
We're going to be trying, yeah. We just came up with 2 good programming assignments for it, so.
Great.
Word completion based on frequency and
Came up
deletion.
with a couple this morning.
Yeah,
in
yeah.
the other class, so.
All right, so binary search trees. So you've done a PA on this also, but it was a while ago. So you definitely want to review binary search trees. So depth and height, right? And remember, these are the number of edges, if you like, from the root to a leaf. So 1, 2, 3, 4, that's a depth of 4. Okay, it's not a 5. We've got 5 nodes here, right? But it's a fence post thing. It's 1, 2, 3, 4 edges from the root to here. That's a depth of 4. Which is why a tree with just a root, the root has a depth of 0. Right? Because you don't have to travel along any links to get from the root to the root. And so the height is the maximum depth. So if this was the entire tree, that would have a height of 4. If this was the entire tree, that would have a height of 0. And the edge case where your tree is null, there's no nodes, but the height of the tree is -1. If we said the height was 0, it would imply that there was a node of depth 0, which would be the root, but there is no root because the tree is empty, so we make the height -1. Almost like a flag, but it's a fortunate flag because it makes the recursive algorithms work perfectly. Roots are still in the ground. So depth and height, balance. So what's the definition of balance? Someone who doesn't know it. No, go ahead.
How does that work?
Tree is balanced,
Left tree and the right tree have the same height.
and they're balanced.
And they're balanced.
Yes.
Right? So you got to have both of those things, or the tree is empty. Okay, so null tree is balanced. If it's not null, height of the left and height of the right have to be within one of each other, and the left tree is balanced and the right tree is balanced. Okay, 3 things have to be satisfied there. If all of those are true, then we can say the tree is balanced. All right, traversal. So depth first traversal, left node right left right node are the 3 usual ones we do. And they're just recursive in their definition. To do an in-order traversal of a tree, do an in-order traversal of the left subtree, then print the root, then do an in-order traversal of the right subtree. Okay, so that's LNR in order. If you want to do node left right, print the root, do a node left right on the left subtree, do a node left right on the right subtree. If you want to do post order with a node at the end, do a post order on the left subtree, do a post order on the right subtree, and then print the root. All right, so it's completely recursive, and if the tree is empty, you don't have to print anything. All right, searching. So that's a binary search tree. Everything to the left of a node is smaller, everything to the right is bigger. If you want to search, there's 2 approaches. You can iterate. So if we want to find the number 45, start at the root, 45 is bigger, move to the right. Look at 42, 42 is smaller, move to the left, there's our number 45. Or we can do it recursively. So if this is equal to the number we want, we found it. If it's smaller than the number we want, call your search routine on the right subtree. If this was bigger than the number we wanted, call your search routine on the left subtree. And if it finds it here, then it found it in the original tree. If it doesn't find it here, it can't be in the original tree because it had to be in this subtree because it was bigger than the root. So we can code search recursively, or we can make a while loop and just start at the root and march down. All right, same thing for insertion. If we want to add a 27, right, start at the root. 27 is bigger, so come over here. Did I not make a good tree? There we go. Is that what you were looking at?
Yeah.
Okay.
I just assumed I had it.
Yeah. All right. So if we want to add a 27, it's bigger than 17, move to the right. It's smaller than 42, move to the left. It's smaller than 40, move to the left. Hey, we're out of space. There's our 27. So that's an iterative version of insert or add. March down the tree like if you're searching, but when you get to a spot where you're going to go one direction and there's nothing there, that's where you add your new piece of data. Or you can do this recursively. So if the tree is empty, just make the root equal to your number and return it. Otherwise, if your number that you're inserting is bigger than the root, insert it into this right subtree, and then just change 17 to point to that new subtree that you've inserted into. And if it's smaller, insert it in the left subtree and change 17's left child to point to that new tree. All right, and then deletion. So deletion, I'm going to stick to the algorithm that we used in the PA and that we used in lecture, which is if you want to delete the root, find the largest node in the left subtree, move that to the root. Okay, and moving that to the root means
So 5 cases and 2 are recursive.
means a lot of cases, yeah. But ultimately it means finding the largest thing here, changing this so its left child points here, its right child points here, and then having this thing's parent adopt this largest node's left child. Okay, so you got to do a few things. You got to do this adoption, and then you got to change the left child to point to that, and the right child to point to that, and then you just free the old root. If you want to delete somewhere other than the root, do it recursively. Okay, if it's smaller than the root, delete from the left subtree and change the root's left child to whatever the new tree is, and same on the right. So you've done that, please ask if there's questions about it. All right, remember hashes?
I had some for breakfast.
Yeah. So this was a while ago, but generally we have an array. Let's just say it goes from 0 to n minus 1. So it's got n entries to it. And we have some hash function which takes a key and it gives us back a number between 0 and n minus 1. So it takes a key which won't necessarily be an integer, it could be a string, could be an entire program, could be a universe, but it turns it into an integer that can be used to index this hash array. And whatever index we get back, that's where we're going to store whatever this key corresponds to. Okay, so you remember the basic concept there? I'll take that as yes. So then it gets confusing if you have collisions. If we hash a key and it says we should store your data in index 3, but index 3 already has something stored in it, then we have a hash collision. And we need to find a different place to store this new key. So we use the probe. So our hash function gets a second argument. And the first time we hash, we set the probe to 0, and that's what gave us our index of 3, which caused a collision. So now we're going to rehash, but with a probe of 1. And the idea is each time you change the probe, you should get a different location back from the hash function. And it should be a location that, based on the key, will hopefully not be the same thing that you would have gotten with another key. So it spreads out the locations where you might store this key. Store the key or the data associated with it. All right, and if you get a collision with a probe of 1, you go on to a probe of 2, and so on. And a good hash function, you'll end up trying every possible location in the hash. And if every location is filled, that's it, your hash is full. You can't store anything more using probing. And so you need to make a bigger hash or something. The other option is to use chaining, where when we hash to a particular location, that's actually something that goes into a linked list. and each thing that hashed to that location gets stored in a new node in the list. And that we can grow indefinitely, but it deteriorates your performance if these lists get really long, because then you end up searching sequentially through here. All right, details come in when you delete from a hash, because if I have key 1 and it hashed to location 3, and then I have key 2 and it also hashed to location 3, and so I rehashed and it ended up getting stored down here. Well, when I search for key 2, I'm going to hash it and it's going to give me location 3. I'm going to say, hey, that's not my key 2, but something else is there. Maybe I had a collision when I stored key 2. So I'll hash with a second probe and that'll bring me down here. There's my key. When you delete key 1, we need to remember that there was something stored here. Otherwise, now when I search for key 2, I'll hash. I'll get a 3. I'll look in location 3. 3 is empty. And I'm going to say, oh, it's not in my hash. And that's erroneous. I need to know something was here and could have caused a collision, so I rehash with the second probe, come down to the new location, there's my key. So we needed to keep track of a deletion state as well as an in-use state. So that was the other minor detail. So that's deletion and deleted flag, collision management, probing, multiple hash attempts. All right, stacks and queues. So I want you to understand the concept, right, as an abstract data type of how a stack and a queue work. I will probably avoid asking you implementation details because you already did that in a programming assignment, right? But high-level behavior, when you put something on the top of a stack, it goes in front of everything else that was already there, so that if you say pop from the stack, that's the thing you're going to pop. Okay, a queue, when you insert something in the tail of a queue, you're not going to see it again until everything that's already in the queue gets removed. Okay, so the queue is first in, first out, last in, last out. Right, so the last thing you put in is the last thing that's going to come out. A stack is a FILO or a LIFO, last in, first out. Okay, so be clear on those differences. You should know recursion. Did I not put lists on here? Oh, linked lists. Okay, good. So recursion, right? We've obviously been doing a lot of recursion, so you should be comfortable with that. Understand the concepts of it, right? Because I'll probably have you write some recursive code different from what we've been messing with in here. Abstract data types. Yeah, like I said, stacks and queues, you should know those as an abstract data type, but also think about lists and trees and tries and things like that, right? And here's a classic example of an ADT, right? So are we using probing? Are we storing things using chaining and a linked list and such? That's immaterial, right? The person using the hash doesn't want to worry about those details. They want to say, here's a piece of data, go ahead and store it in the hash. Hey, tell me if this piece of data is in the hash. Hey, give me a list of everything that's in the hash, print it out, right? They don't want to know about probe numbers and probe attempts and deleted flags and all that kind of stuff. So as an abstract data type, a hash is just a way to store information associated with keys and then put in a key and get back a piece of information associated with it, aka an associative array. All right, so abstract data types. Makefiles, you've been doing makefiles, so I probably won't ask about makefiles, but you should know how to do makefiles. GDB, I probably won't have a GDB question because we've already done that, but I want people to know GDB when they leave here. So maybe I'll do a GDB question, I don't know. Malloc free and Valgrind, right? So you wouldn't have gotten this far without being pretty good with malloc. And free just undoes a malloc. Right, so it releases it, and Valgrind lets you figure out what's in there. Pass by value, pass by reference, star, ampersand, dot, arrow, right? You've been using those things. I don't think we need to talk about them. Structures you've been using. So linked lists, what do you need to know about linked lists? Basically just the general setup of a linked list. We usually have a sentinel node in the beginning. We don't need one, okay? It just means there's some edge cases if we don't have a sentinel. It's an implementation detail. It's nothing to do with a linked list as an abstract data type. Linked list, insert this thing, find this thing, delete this thing, print out all the contents in the list, stuff like that. Okay, but implementation-wise, if you have a sentinel, if you don't have a sentinel, there's differences, right? Basically having to do with making the list completely empty. Is it a null versus a sentinel is pointing to null? W-linked lists, right, just have a pointer going forward, pointer going backward, makes it a little faster to do things like insert and delete, because we don't need to keep track of the previous node as we're marching forward or look ahead 2 spots, right? When we get to a node and we say we want to delete this, we can find the prior node using the previous pointer and then get that to skip over the node we're deleting. And order of complexity of list operations was just looking at list versus arrays, right? That was our original setup for why we wanted linked lists, because arrays it's hard to insert in the middle because you have to move everything down. The linked list it's painless. Make a new node and just have the previous node point to the new one, have the new one point to the thing that comes after it. And they're not required to be sequential in memory, so we don't have to move things down to make space for a new node. And the same with deletion. We don't have to move everything up to occupy the space wherever the number we're deleting was stored. We just don't point to that number anymore. All right, so what should you be prepared to do? So I might have you write some snippets of code to do things like set up a structure, manipulate fields inside a structure, dynamically allocate a structure, free a structure, who knows? I haven't written this yet, but I got some ideas. I might ask you to analyze some code. So here's some code and show me how it modifies these structures, show me the value of this thing after this executes, that sort of thing. Or I might give you some code and ask you to tweak it. So here's some code that does this, change it to do that. I don't really want you writing pages and pages and pages of code for this. Okay, that's time consuming on a timed exam. It's and it's not particularly illuminating. So short snippets will probably be the theme. Okay, it may only be 4 or 5 lines of code, but there'll likely be 4 or 5 lines of code you've never written before in this particular way. Okay, so you're going to actually be writing this stuff instead of remembering it. Analyze performance of algorithms, probably not a whole lot of that. I might ask you something about big O of a bubble sort or something, but that's not a huge part of this, I don't think. Recursive code is, however, so again, analyzing, writing, and or modifying recursive routines. I might give you a recursive definition of something and ask you to write some code to make a function that uses this definition. I won't ask you to make a big, horrible recursive tree that shows me all the calls of something, right? But I could ask you some conceptual questions. I could give you some code and ask you to add caching to speed it up. That's always fair game. So probably a fair amount of recursive code. Understand and operate on lists, trees, tries, hashes, stacks, queues, and other data structures. So I could give you a hash implemented as an array. I could tell you what the hash function is. I might have some data stored in there, and I might say, show me what happens when you try to store this particular key. And you'd want to run it through the hash function. If it's got a probe, run it through with a probe of 0. This comes up with this number. There's a collision there. I'll run it with a probe of 1. That spot's free. This is where it'll get stored. Okay? And you want to keep in mind that you may not always get the right answer, but if you're doing the right thing, that's worth most of the points. So that example I just gave where you were hashing something and doing multiple probe attempts and such, if all I see is this gets stored at location 7, and that's not the right answer, you can't really get any points for that, right? If you show me I'm going to set probe to 0, I'm going to hash this, and I'm going to get a 3, and there's a collision, I'm going to set it to 1, right? and maybe you start with probe equal 1 instead of 0, right? That's most of the points, right? You're using the hash function, you're checking for collisions, you're continuing to probe. That's most of the points right there. You started with 0, or you did an error when you added up the digits and you got a 12 instead of a 13, right? That's not a big deal. So if you can show me what you're doing within reason, right, that's helpful if your final answer is not exactly right. But you don't have to go crazy, right? Show me every single detail. But the stuff that shows me you understand what you're doing, that's always helpful. So inserting things in trees, deleting things from trees. We talked about tries, maybe telling me if a word's in the try or adding a new word to a try. Hashing some things. Here's a stack. Show me what happens when you say push this or pop that. Same with queues, stuff like that. Conceptual questions maybe on GDB, Valgrind, Makefile, some of these tools. That's a little more 224-ish. And I'm pretty comfortable that most of you have been using these things, especially GDB with PA5. More and more people are coming to me and running through GDB on their code, and that's really helpful. It really, really will help you down the road. And there's a Java version, JDB, for Java for 223. There's actually some nicer debugging tools for that also. And then sorts. Tree operations, hash operations. Yeah, so I could give you a set of data and say, show me the first pass of a bubble sort. What's the data look like in the end? Or show me how this array of data would be treated in a merge sort, first pass through a merge sort. Right, so one recursive call to merge sort, so split it in 2 halves, and this will get called. This will get sent to merge sort, this will get sent to merge sort. Or I might give you 2 arrays and say, show me how you would interleave these. I don't know. I've never done that for merge sort. That sounds hard. But here's a set of data. Show me the first 3 values that get put into the output file if you do a selection sort or an insertion sort. Or a quick sort's always a good one. Right, so do a quick sort down to the point where the pivot's in the correct location. Makes sense? Hopefully nothing that's different from what you've already been doing and working with for the past 10 weeks now, right? Questions that you have not seen before, but the concept should be things that you've been doing and doing a lot of for the most part. So I think it's 4 pages double-sided of notes, 8 pages single-sided. I may or may not be here. So if I'm in jury duty, Scott will give you the exam. And this section would be Monday at 12. If for some reason you'd really rather take the Wednesday 11 o'clock exam, you can do that. That's fine.
So is the exam going to be like 16 minutes or
110.
110?
Yeah. So it'll be long, but pace yourself. And if I say write a function, you don't have to write a main program. Right? If I say write a main program, then you need a main program. But if I say write a function, you can just write a function. If I say write a few lines of code, you don't need to put it in a function. You don't need to put it in the main program. Right? I just want to see a few lines of code. If you need to use a temporary integer, you've got to declare it integer, temporary integer, or whatever. Right? But a lot of these will probably be pretty focused on just show me how to do this thing. And you can get away with less. Good? Okie dokie, cool. Any other questions, or I'll let you out 3 minutes early? Bad timing on my part, I know. All right, cool. Well, I will see you in 2:15 or in office, or I will see you for your final.
So I didn't see on the 3D printer thing for the website.
Oh, well, let me get you a.
So I want like.
Let me get that information for you.
I'm gonna put this link. There should be